Hey again to everybody. I hope you are all doing well. And this is now the fourth video that we will have for discrete math. And just a quick review again of the things that we have finished so far. Definition of proposition. We have our connectives. And then our truth tables. Then finally, last time, we had our rules of replacement. So before I proceed with our lesson for today, actually I'll be giving some more examples for truth tables and at the same time rules of replacement. So we will be considering some examples today. We will be showing two solutions, one by truth table and one by rules of replacement. Again, as I was saying earlier, please turn now your modules to the rules of replacement. I will not go through them one by one. But remember, last time we had 14. So for today, let me give a few examples. And our first example will be to show that not Q implies not P is equivalent or equal. In some textbooks, they use three lines, meaning equivalent, logical equivalent. But since we have already started using the equal sign, we can stick with this notation. Anyway, that's just for the notation. And then we would now like to show that this is equivalent or equal to P and not Q. Let's do this in two solutions. So the first one is using a truth table. We only have two propositions. So we have P and Q. Of course, the left side, we have not of not Q implies not P. And the right side is P and not Q. Two propositions, 1, 1, 0, 0 for P. For Q, alternate 1, 0, 1, 0. Okay. So what we can do here is maybe we can divide this into several columns. This will now be for the following. This column will represent not Q. So we now negate all the elements in this column. This will become 0, 1, 0, 1. We're just negating this column here. And then for not P, we now negate this column, not P. This will become 0, 0, 1, 1. And then this column will now be for this implication, this conditional statement. And what did we say before? If it's a conditional statement, we look at the first proposition. If the first proposition is false, automatically this will be true. But if the first proposition is true, we have to check the second proposition. If it is true, then this will be true. But this is false, therefore this must be false. This is true, therefore this is true. And then finally, for the column here, it will now represent the entire left side of our proposition. So we're now looking at the negation of this entire thing here. And this whole thing inside the sign of grouping is represented by this column here. So we negate this column. This now becomes 0, 1, 0, 0. So take note, this will now be our final column for the left side. And then for the right side, maybe we can imitate the same thing here. P, 1, 1, 0, 0. So this column now represents P. This column represents not Q. So that will be 0, 1, 0, 1. And then this column will represent for and. And when we're using the conjunction and, both propositions must be true so that this will be true. True and false, this must be false. True and true, this must be true. False and false, this will be false. False and true, this will be false. And this column here will now represent the entire right side. So you will find here that the left side is indeed logically equivalent to the right side, which means we have proven using the truth table that the two propositions are exactly the same. So for today, let's now consider a second solution. And the second solution is using now some of the rules of replacement. So again, as I have mentioned last meeting, the rules of replacement will now serve as like formula. Yun nga, from the term itself, rules of replacement. So if we can find logically equivalent expressions, we can use those rules to replace the existing proposition. Okay, so if we will now rewrite the problem that we had earlier, originally we had not Q implies not P. Okay, so that's the left side. And then the right side is P and not Q. So we can actually rewrite this as this pattern. We can now have the left side as not Q implies not P, which will now serve as our premise. And then we now let P and not Q be our conclusion. Okay, so that will now be our conclusion. So our goal here is, from the premise, we would now like to use some rules of replacement until we come up with the right side of the equation, or that's the conclusion. Did you get that? So let me repeat that. Our goal is to manipulate the premise by simply using some rules of replacement until we reach our conclusion. Okay, so let's do that. Going over our list, I have told you to go to open your modules to your list. The left side of our proposition or our premise now involves an implication. So if you will go over your list, what are the rules involving implication only? So if we will look at the list, we have number 8, material implication. If we are given P implies Q, that's equivalent to not P or Q. Another rule that involves an implication is number 12. Actually, number 11 also. But if you will look at number 12, you have P implies Q is equivalent to not Q implies not P. Not Q implies not P. So, if you will look at number 12, isn't it that this section here is exactly the right side of the formula number 12? Which means, if we will now use that, contrapositive, the terms inside the sign of grouping, so let's just copy the negation here. This will now be equivalent to P implies Q. So what did we use? By contrapositive. So using the contrapositive, we now get P implies Q. Then, after which, we can now consider, again, this is an implication. So going over again your list, we can use number 8, material implication. So using now material implication, you will now convert this as, sabi sa number 8, P implies Q is equivalent to not P or Q. So this is number 8, material implication. Using material implication. And then, so I think we're almost there. We need a P and not Q. You will see here in our last line that our entire group is preceded by a negation. It is preceded by a negation. And where do you find an expression something like that? In your list, you will find that under number 4, your De Morgan's law. And if you will now use your De Morgan's law, since this is an or, you can use the first in the list. And look at the first in the list, what happens? If your proposition, which is having a connective or the disjunction, and it's preceded by a negation, it is equivalent to the negation of the first proposition, and then you now change this to end, and you also negate the second proposition. Again, go to your list. Number 4, the first part. Ang nakalagay doon is the negation of P or Q, it's equivalent to not P and not Q. So, we negate this. And isn't it, we also have what we call the double negation. So, if we have not P, then that must be P. This now becomes and we now negate that, not Q. So, what did we use here? De Morgan's law. Then after using the De Morgan's law, it's already what we want, P and Q. So there goes the proof of this example. So the first one, we just use the premise. By contrapositive, this became P implies Q. Then by material implication, this now becomes not P or Q. And then by the De Morgan's law, we now have not P, which is a double negation, which will give us P. And then end, we negate Q, that's not Q, which is the other side of the expression. So there goes the first example. We have shown that we have a logically equivalent, or we have a proposition that is logically equivalent to another proposition using the truth table approach and the rules of replacement approach. Let me now give a second example. So the second example is show that P or Q implies R is equivalent to P implies R and Q implies. There are 3 propositions. Let's use the truth table approach. I don't know how we will fit this in. We have P, Q, R. And then the left side, P or Q implies R. The right side, P implies R and Q implies R. Three propositions. First proposition, 1, 1, 1, 1, 0, 0, 0, 0. Second, tagdadalawa, 1, 1, 0, 0, 1, 1, 0, 0. Third proposition, alternate, 1, 0, 1, 0, 1, 0, 1, 0. Okay. Let's divide this into, maybe we can just have it there, P or Q. So this column will be P or Q. P or Q, when one proposition is true, this must be true. P or Q, both are true, this must be true. Both are true. P is true. P is true. Q is true. Q is true. Both are false. Both are false. Let's just copy R here. 1, 0, 1, 0, 1, 0, 1, 0. Implication. Implication, if the first premise is false, this must be true. If the first premise is true, second premise is true, this is true. First is true, second is false. First is true, second is true. First is true, second is false. Both are true. The second is false. Okay, so we will now look at this column here for the entire left side. And then, for the right side, we have P implies R. P implies R if the first proposition is true, I mean false, this will automatically be true. If the first proposition is true, second proposition must be true also. So this will be false, this will be true, this will be false. We're looking at P implies R. And then this column will be Q implies R. 1, 1, 1, 1. Why? Because Q falls under those rows. And then Q implies R. Both are true. R is false. Both are true. R is false. And we're now looking at and for this column. Both are true. Both are false. Both are true. One is false. Both are true. One is false. Both are true. Both are true. We now look at this column. Are they equal? 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay. So, they are logically equivalent. Now, let's do the second approach. Let's do the second approach. The second approach will now be using our rules of replacement. So, how do we write it again? So, we consider the left side, P or Q implies R as our premise. And then we desire to have P implies R and Q implies R as our conclusion. Again, we will work around with our premise, and our desire is to come up with our conclusion using some of the rules of replacement that we have. Okay, let's try to observe and what can we possibly use here. The main connective in our conclusion is the conjunction and. The main connective in our premise is an implication. Okay, so that should tell us that we must get rid of our implication here and maybe convert it to an or to an and, whatever we can possibly use. going back to our list, where do you find an implication again from your list? We can look at number 8 again, material implication. So if we will now use the material implication, this entire thing here is now considered as a single element. Like in algebra, when terms are grouped together, we consider it as a single element. In mathematical logic, when propositions are grouped together, we can treat that as a single proposition. Therefore, go now to your list, number 8. Look at number 8. In your list, in number 8, material implication tells you you have P implies Q. P implies Q, and P implies Q gives you not P or Q, right? So the first proposition will be negated. Okay. And then from your implication, it now becomes an OR. Let me repeat that. In your formula, what you have there is P implies Q. And P implies Q is not P or Q. Remember, these are just propositions. Like in algebra, they are like variables. So we can extend our rules using other representations. So again, P implies Q is not P or Q. This is using material implication. By material implication. Then after using our material implication, what else can we do there? Okay, so maybe we can get rid of this negation here. Since these propositions are grouped together and it is preceded by a negation, and the connective here is a disjunction, we can use our De Morgan's rule. And De Morgan rule states that if we have a conjunction or a disjunction preceded by a negation, we can distribute the negation to our propositions and then change your connective. If it's a disjunction, it becomes a conjunction. If it's a conjunction, it becomes a disjunction. And then that's our R. This is now by De Morgan's law. Then after using De Morgan's law, where are we now? Okay, so I think we can go again to your list. We can use here distributivity. Look at this. Distributivity law. We have distributivity of OR over AND. So we can actually interchange this distributive property, but commutative property. But anyway, by distributive property, so if you will imagine distributing R to each of this, we now get not P. Okay, so we're looking at the distributivity of OR over R. So we now get not P or R and not Q or R. Oops, that should be let me erase that. That should be not Q or R. Distributive property. Distributive or distributivity. Okay? So we're almost there. Look at this. You have a conjunction, you have a conjunction, you have PR, QR. So almost there. But in our final conclusion, this is an implication, but we have here an or. What can we use now? Look at your list again. Remember, in your rules of replacement, there are two sides, left and the right. You can actually work from left to right or from right to left. Since we already have proven that the rules of replacement are equivalent propositions, they are interchangeable. You can use the left going to the right, or you can use the right going to the left. Therefore, if you will look at this line, you can again use material implication. But instead of doing it from left to right, we can now have it from right to left. Look at your material implication, number 8. The right side there is not P. Look at the format, not P, or nakalagay dun sa formula is Q. So if you will replace Q by R, right? Pwede, di ba? Not P or Q. And not P or Q, according to material implication, so this now becomes P implies, our Q is R, so magiging P implies R, which is already this one. And using again material implication here, that gives us Q implies R. So this is again material implication. So there you have it. So we have seen two examples today of propositions that are logically equivalent. So we can use the truth table or we can use the rules of replacement. So you might be saying, mas madali yung truth table. Well, maybe I will agree with you that the truth table is easier. Well, it's just more tedious, but what if the instruction will tell us to prove the proposition using rules of replacement? So we have no choice but to follow the instruction. Okay, so I think the two examples will be good for today. And maybe for the weekend, I can post some more exercises for you to work on. But since Monday and Tuesday are holiday, then I will respect your time. You can use that as really a time for rest because it's a holiday. Okay? So for the meantime, I will stop here. So happy weekend and enjoy again listening to this video. So one advantage of what we are doing now is you can rewind every now and then if you want to go back to a certain portion, or if you want to go over through the entire lesson, you can easily go back to the link. So once again, God bless you. Have a blessed weekend.